So here's an igneous rocks and processes summary. So we're going to put it all together. It starts off with the rock cycle. The rock cycle identifies how a rock is not the same rock eternally. It's not forever. To become an igneous rock, something must be melted. So generally we call it magma when it's in a liquid stage within the earth, and that's lava on the earth's surface. But a sedimentary rock is something that's broken down. It could be rock fragments or it could be dissolved in water or solution. So sedimentary rocks, the process is different than igneous rocks. And to become a metamorphic rock, something must be changed by added temperature and pressure. Hopefully you realize it's not enough temperature to melt it. If it melts it, it's an igneous rock. So we have this process here. There's no one point, it's just a process. It's simply cycling from one to another. It can be igneous, can be metamorphic, can be sedimentary. All different means in which it becomes each type of rock. We're focusing now on igneous. Igneous implies it formed from fire, but not literally, more just a liquid phase. It's enough temperature to melt the high melting point minerals, and so that's a liquid, and that's what we see here in this picture. So it's a process, and it can travel from one form to another. We've looked at different igneous rocks by their texture. Each texture is the result of the conditions which form the rock. Here we have a fine-grained, here we have basalt. Here we have a coarse-grained granite. Here we have a glassy and let's just call this a vesicular pumice. And here we have a porphyritic rock that has two stages of cooling. Each one of these has a little different formation. Each one of them has a different texture. We also looked at fine, we've looked at coarse grain, we've talked pegmatitic with pegmatite itself, just large crystals that are an inch or larger, or 2.5 centimeters. We've talked vesicular, we've talked porphyritic, and we've talked glassy. And our example for glassy was more of the obsidian type. So igneous rocks have different compositions and textures. When we use the term granitic, it implies it is very, very much felsic. And it would fall in this column of information. So this vertical column here should make sense to you. When I find something, it's going to be high in silica, right? 70+% silica, and little iron and magnesium. So we're using these arrows to further make sense of the composition. We can talk intermediate rocks. They have less silica than felsic, but here's my column here. I'm looking at my intermediate. Sometimes they're referred to as andesitic, but we're not going to do that much with intermediate rocks, so I'm not even going to get into the andesitic part. But notice, relative to felsic, it's going to have less silica and more iron and magnesium. And here are my compositions, right? You're going to need to be able to interpret what's in here. Generally speaking, you'll need to know the most common or the minerals components within the rock themselves, and you can use this to make sense of it. And even relative percentages as well. Here you can see quartz and case bar dominate here my felsic rocks, whereas plagioclase feldspar, in this case sodium rich, dominate my intermediates, along with some quartz, some case bar, little pyroxene, and amphibole. So a basaltic variety, right? Basaltic variety. These have lower silica content than your intermediate. They have higher iron and magnesium than your intermediate. So notice I'm talking relative, because I could say that mafic are going to have more silica than ultramafic, and they're going to have less iron and magnesium than ultramafic. So understand, I'm traveling from left side to right side here. My mafic themselves, so the basaltic variety, mafic dark colored, these have even less silica than your intermediate and more iron and magnesium. And here I could see calcium rich plagioclase feldspar, I could say olivine, you'd see pyroxene and amphibole. And lastly, my ultramafic. Ultramafic here, very dark, have even less silica than mafic rocks and a greater abundance of iron and magnesium. And then down here are just a couple different examples. Here are my phaneritic rocks, and here are my aphanitic rocks. So when I look at igneous rocks, I look at a cross-section of the earth. Igneous implies that the rocks have solidified or crystallized from a liquid state to a solid state. Magma is liquid rock inside the earth. Lava is liquid rock on the earth's surface. The liquid rock material within the earth comes from a very, very hot interior. And once the minerals in a rock cool under their melting points, they solidify. And this is where Bowen's reaction series comes into play. That polymineralic rocks, right? Most of the rocks we've looked at have many minerals within them. They solidify at different rates based on the minerals that are contained within them. So as I look at Bowen's reaction series, I'm going to go back to this statement on the previous slide. Polymineralic rocks solidify at different temperatures based on the minerals contained within them. So you'll find that higher temperature melting points are going to be olivine and calcium-rich plagioclase. And lower melting point minerals are going to involve quartz, muscovite mica, and case bar, potassium feldspar. That the lower melting point minerals happen to be felsic, right? Granitic variety. And your higher melting point are going to be ultramafic and into your mafic particular varieties. So when I look at this, as a magma is cooling, right, the down arrow, it's cooling in temperature, you get a different sequence. My discontinuous change says that olivine is completely different chemistry than pyroxene, which is a completely different chemistry than amphibole and B mica. So this is discontinuous. These are altogether different minerals together. They just have different ingredients within them, and they look different structurally as well. Whereas my continuous series, this is all plagioclase feldspar. Just up here, it happens to be of the calcium-rich nature, and down here at the lower melting points are going to be more of the sodium-rich. So this is a continuous series because it's all plagioclase, just difference in calcium and sodium. And these are discontinuous because these are completely different minerals altogether. And when we look at these minerals here in the felsic range, you're going to find that these minerals here are going to be the first to melt out as we create continental crust from oceanic crust. So polymineralic rocks solidify at different rates based on the minerals contained. So let's look at how basalt and granite form. We should know that basalt forms when ultramafic magma, right? It comes from deep within the earth. It rises or upwells to the surface. Well, the deeper I go, the hotter the temperatures and the more ultramafic the mineral composition are. As it rises, some of the olivine and calcium-rich plagioclase separates out, it crystallizes. So you go from this ultramafic mantle rock magma to, let's just say it has less olivine and less calcium-rich plagioclase, and it's going to be left with pyroxene, a little olivine, and still plagioclase, and it's going to form basalt. And this rock here is going to rise and crystallize. Because it crystallizes quickly, it's going to be fine-grained. Well, by now we should know that our Earth's crust is dynamic. It is moving. And as it converges with another plate, in this case continental crust, it's going to subduct. Right? Oceanic crust high in iron, high in magnesium is going to be denser. Hopefully you realize denser materials sink. You put a rock in water, it's going to sink because it's denser than the water itself. So the same rules apply to oceanic crust. It sinks as it subducts. We're simply running Bowen's reaction series in reverse. If this is a solid rock, you're going to melt out or sweat out, right? The remelting of basalt melts out low melting point felsic minerals, forming granite. So as this reheats up, it's traveling back inside the earth, high temperature, high pressure. You're going to melt out your quartz, your muscovite mica, and your case bar, your potassium feldspar. So this is the result. Granite is the result of applying Bowen's reaction series to a mafic particular rock. In this case here, basalt. By melting basalt, you're going to get a process of partial melting to form this particular type of magma. So let's look at a magma chamber itself. We haven't spent a lot of time looking at it. We're simply just talking about a region of liquid rock inside the earth, and we can apply Bowen's reaction series to it. So if I have this liquid rock here deep inside the earth, it's going to be high amounts, it's going to be relatively ultramafic to mafic. Right? The early formed olivine crystals at the top of this is going to be lower temperature than at the bottom. Well, they're going to crystallize out. And this crystallization, olivine in this case here, is going to be denser. It's got a lot of iron in it. Iron's going to sink. So you're going to have these crystals settle to the bottom throughout the non-viscous magma. So it's going to sink out. Boom. So this magma just became more felsic, right? And the bottom part of the magma chamber is going to be more mafic. You simply have the application by losing iron and magnesium. In this case here, by separating this out, you now have a liquid magma chamber that is just chemically changed. So you're going to form new minerals with the residual magma. It's just going to crystallize a little differently. And then the longer time, the greater amount of time, the crystals remelt in the hotter and the lower magma, making it more mafic. So it's going to travel down here. It's going to let's just say reform a new composition. So down here is going to be a different composition than up here. So here was a drawing that we did. That magma composition A, ultramafic, can become a magma composition B of felsic as it crystallizes. And notice it's cooling as I travel from left to right. And here I go from ultramafic. Here it travels and crystallizes out my olivine. It becomes more mafic. Well, when I say mafic, that's actually less iron and magnesium because you've gotten rid of olivine. When I get rid of my next particular mineral, pyroxene, you're going to continue to have a liquid rock, but you're going to have a different mineral sequence. You're going to have a different chemistry in which is going to crystallize. And lastly, as I continue traveling here, I can go from this intermediate form to the final felsic phase. That this is called crystal settling, viewed applying Bowen's reaction series as a magma chemically evolves. And this is the final slide that you really need to make sense of, that different minerals have different complexities to them in terms of their silica structure. So olivine is the first to crystallize out, the highest temperature. So you're only going to form these single tetrahedra. It's a very simple network of single tetrahedra grains of olivine. However, once you've gotten rid of olivine, you have a new composition of magma that's going to crystallize. Then you get pyroxene. These are going to form in single chains. It's a little bit more complex. So a cooling or evolving magma is going to get more complex in its structure. So here we have single chains, amphibole. Next line is going to have a sequence of double chains. Notice double chains are more complex than single chains. You keep on cooling, you get B mica and your micas. These are sheeted. Notice these are even more complex yet. You start putting together double chains, you create sheets. And last but not least, you get your feldspars and your quartz. And these are three-dimensional, 3D networks that are just more complex. So when I apply that to Bowen's reaction series, we can talk about single tetrahedra of this group right here of olivine. We can talk about your single chains of pyroxene. Right, here's your pyroxene. You're going to get double chains of amphibole. Bingo. We can apply that here. Amphibole here. We can get your sheet networks. Right, your sheets are a little bit more complex. B mica and muscovite mica. So here's my B mica. Here's my muscovite mica. And lastly, your most complex three-dimensional networks are going to be quartz and technically both of your feldspars. They still have a high amount of silica within them. And so therefore, all of your feldspars and quartz. So your plagioclase, your K-spar, and your quartz. That this picture here, this sequence here is just getting more complex from your high melting point, and as I continue traveling down here, it's cooling, had lower melting points, and they're going to have a different compositional structure or network altogether.